All right, class. Today I've dressed up fancy, with a nice shirt on. Um, I guess that means this lecture is super important. Today we are talking about logically equivalent statements, which we hinted at last time when we talked about biconditional statements. But the idea there was that they were just two specific statements that happen to be the same. But here, what we are doing is we're saying that two statements. And what we mean by statements now are things you can build up by using logical operators. So you can do like P and Q, and you can throw negations in there and if thens in there. So two statements like that, where the P's and the Q's are not specific things, um, those can be logically equivalent to, and oops, logically. And so we say that they are logically equivalent if what we define logical equivalence at is wait, sorry, let me say that sentence again. What we define logical equivalence as is having the same truth values, meaning that they are both true at the same time and they're both false at the same time. When you consider the independent pieces of the statements, P and like if P, Q, and R are the base statements, and you throw them together with a bunch of different symbols, then you see if that big concoction is true or false by looking at when P, Q, and R are true and false. And then you do some other concoction and you get the same true and falseness, then they're the same. Okay, so it's much easier to see with an example. Also, I didn't write the notation. So, and we write this to mean logically equivalent. Suspiciously looks like an equal sign with a third line on top of it, because it's sort of like equality of logical statements. Okay, so here's the first one. So notice I'm not giving you a specific P and Q. This is just true for any P, any Q. If you stick them together in this way, which is you and them, and then you negate that result, that's going to turn out to always be exactly the same as if you negate each one separately and then you OR them. So it sort of looks like a negative distributing over an operation. Like if you did negative 3 plus 4, you might think that would be like negative 3 plus negative 4, and that's correct for numbers. But here, it's like the plus is turning into a different operation. So it's a bit weirder. Okay, so let's, whoops, why did it do that? And we can show this by calculating the truth tables. So what we'll see is they are both true and they're both false at the same time. All right, so they're both dependent on P and Q. So what that means is I have to consider all four possibilities. So they could both be true, one could be true, the other could be true, or they could both be false. And then I can build up these two things. Okay, so first I'm gonna need a P and Q column. So how does and work again? It's true only when they're both true. One is not enough. So then you get true, false, false, false. How does negation work? So when you negate something, it just becomes its opposite. So whenever the previous one was true, now it's false, and vice versa. Okay, so that is the truth table for the left side. So what this is saying is you're always supposed to connect it back to the original P and Q. This is saying if they're both true, then this big complex thing we just created is false. If this one's true, then that one's true. If Q is true instead of P, we're still good. And if they're both false, we're still good. Okay, so we're always looking back to the first two columns. to see what's going on. All right, so now we need a whole bunch more columns. We need not P, so we can calculate the right side. So I have to look all the way back at the P column, and I have to say, okay, it's the not of that, so it's going to be opposite. False, false, true, true. I also need the negation of Q, so it's going to be false, true, false, true. That's the opposite of the Q column. And now I'm going to OR them together. So when is that true? That's true if either one is true. Okay, so in the first spot, I'm looking here, neither is true, so the OR is false. But everywhere else, at least one of them is true. And what do you know? I get false, true, true, true. So they have the same truth values in the same situations where P and Q are telling you the different situations. And this is independent of what P and Q are actually saying. As long as they are statements, this is true. It doesn't matter what statements they are. And that's the cool part. Okay, so that's one. We can think of this sort of as like a law or a rule that you can use now. Meaning if you see something in one form, you can rewrite it in the other form. In English, it's sort of harder, so maybe we'll save this for later. Let's do some more. Okay, so this is like the opposite of what we just did. Now I'm going to negate an OR. Oops. And it's going to do sort of the opposite thing. It's going to, again, negate both. And it's going to flip the logical operator upside down. So the OR will turn into an AND. So to compare that to what we just did, the AND turned into an OR. And you negated both. Same thing happens here, except OR turns into AND. Okay, so we can do the same exact thing. And it'll work just fine. So there's that. All right, so now I have to OR them. So that's 3 trues and a false, and then I have to negate that. So it's going to be the opposite, false, 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 true. Okay, there's the left-hand side's truth table. Now on the right-hand side, I need these negations again. So just the opposite of the first column. And this is the opposite of the second column. And then I AND them together. So now I'm looking at these two columns and I'm saying I need them both to be true for it to be true. So that only happens at the very end. So once again, these are the same. So they are logically equivalent. Okay, so these two laws that we just proved are called De Morgan's laws. De Morgan's laws. So, oops, laws. So I will tell you, I'll rewrite them here, just so you have them in one place. But the basic idea is you can sort of distribute the negation through, but it turns AND into OR and vice versa. So remember that laws work both ways, which means if I start on the right side, I can also go to the left-hand side. So you could also think of this as like I can factor out, if you like that phrasing, factor out a negation, but it's going to flip the logical operator upside down. Okay, so these are called De Morgan's laws. They're two of many laws. They're different than how negatives work with regular operations for numbers, so that's interesting. Okay, so let's see, what's next? So yeah, I just wanted to also mention one more time that we use this guy when talking about general statements like above, where we don't have specific things going on with P and Q, versus this double arrow thing we did last time, the biconditional, which is for specific statements. that you show are the same. Okay, so let's do another example. This is another interesting example because it tells us another way to think about the if-then statements. So it turns out that the if-then statement you can think of as an or statement instead. So this one I will give a little example in English once we finish calculating it. Okay, so it's nice because it gives us an alternate way to think about implies or if-thens. Okay, so again, both sides are just dependent on P and Q, so I have to write down all the possibilities that I can have. And then I got to build each thing. Well, let me do the right-hand side first this time because I just know it off the top of my head because it's sort of weird and people always forget it. I guess that makes me remember it more. So it's true if they're both true. It's only false if the conclusion does not come from the hypothesis, but if the hypothesis happens to be false in the first place, it's automatically true. Okay, so that's what we're going to hope the left side is the same as. So I got to build it up. So I got to have my negation of P so that I can use it. And then I will OR that with Q. So now I'm looking at these two columns here. I'm ORing them together, which means that it's true if either one is true. And what do you know? It happens there, there, and there. So it's exactly the same as this column. So this one is very interesting to think about. It's going to help us a lot. So let's think of a little example. If it is raining, then the grass is wet. Okay, let's assume that this is a true statement. I believe it's true. Let's try to think of it in this other way now. It's supposed to be exactly the same. So what is this other way of thinking? It's saying it is not raining or the grass is wet. So can you see how these two statements are saying the same thing? The best way to think about it is just assume they're both true and relate what they are saying. So if this first statement is true, what it's saying is, if it is raining, then the grass must be wet as a result. But that's the same as saying, well, either it's not raining or the grass is wet, because if it were raining, I would automatically know that the grass is wet. That's what this stuff is saying. So it's exactly the same as saying, well, either it's not doing that, or if it were, that would mean the grass is wet. So it's either not raining or the grass is wet. So I would advise you to write out a couple more sentences in both ways and try to convince yourself that they're saying the same thing. Okay, because what we're going to do is we are going to move on and we're going to play around with these things in sort of an algebraic way. So the nice part is we can string together logical equivalences, sort of like equal signs can be strung together. And then we can treat statements symbolically and calculate things. It's a very vague sentence, so let me do an example to say exactly what I mean. So what I mean is something like this. If I want to do another one of these proofs, I haven't said the word proof yet, but that's what I was doing with those truth tables. But if I want to show another logical equivalence like this one, this is another one, I don't have to draw the truth table because I can rely on things that I already know. I can rely on the laws I've already established. And that's a perfectly acceptable way to prove something because we already established the other laws. So let's go through this. So how can I do it without truth tables? Well, since I just learned how to rewrite this guy as something else, I might as well use that. So what was that again? If P then Q is the same as saying not P or Q. So I already know that this is a rule. Okay. So then what can I do? Well, I'm trying to learn about this thing, and it sort of looks like we already have, except has a negation in the front. So why don't I just do the negation on both sides? Well, why is that okay? It's because if two statements are the same, that means that they are both true and false at the same time. So that means that their negations are both true and false at the same time. They're just the opposite of the previous. So that is okay to do. And then I can continue going on this right side here. What can I do with this thing? Well, we actually saw something that we can do with that already. We can use De Morgan's law. So I know how to distribute a negation through an or. I just have to remember to turn the or into an and. So then I get that. Oh, whoops. I forgot that there was already a negation here that I erased. So actually now, this guy has two negations. Okay, so what can I do then? Well, a double negation, you might assume correctly that it cancels, and it does. And why is that? Well, it's because not P is true when P is false. So that means not P is false when P is false, and true when P is true. So they're the same. What is this? Yeah. So that's what we're using here. Okay. And then I think we're done, right? That's what I wanted to show. That's what I got over here. So this ends the proof. So we don't have to use truth tables. You can use previously established laws instead. Okay, so the next law we're going to show is very important for the future. And that's why we're going to do it. So it has a fancy name. It's called the contrapositive. The contrapositive, the statement, or I guess a conditional statement, if P then Q, is the statement that you get by switching the order and also negating each one. I don't know why I made the arrow so long. That's not part of it. And it turns out that it's the same as the original statement. So this is a very interesting thing that happens here. And you could sort of convince yourself through some examples right now. So like you could say, if it is raining, then the grass is wet. And then you could try to create its contrapositive. So what's the contrapositive in this situation? It's, well, I switch Q, this is Q, and I switch P, and I negate each one. So if the grass is not wet, then it is not raining. So if you write out some more sentences like this, I hope you can see how these are saying the same exact thing, how they're equivalent. if it is raining, then the grass is wet. If that's true, then it's also true that if the grass is not wet, it must not be raining. It's saying the same thing in a different way. So this relationship will come in handy later a lot. So let's prove it right now, though, just to see more practice doing these little mini proofs. Okay, so here it is. We already know that this guy is the same as something else. We already did that earlier. So what was that? It was the same as, it was right here. We used it, and we initially set it up here. So it's the same as saying not P or Q. And then we're gonna have to pull a bunch of little tricks. So we're trying to get all the way to this thing here. So how are we gonna do that? This one is a bit tricky. The first trick we're gonna pull is we're gonna realize that if I say this or that, it's the same as saying that or this. So there's no reason that these two have to be different, so I can just switch them. In fact, this is another logical equivalence that's true that I haven't bothered to prove, but this will always work. This is called a commutative law. It's just like for numbers. 3 plus 5 is the same as 5 plus 3. So in that way, the OR operation is the same as a plus or times operation. Okay, so I'm just going to switch those. You don't need to do that step. It just helps us see what's happening better. And then what I'm going to do is I'm going to introduce a double negative. The parentheses is not really necessary. It just helps me see better what's going on. So that's the same because of what I used earlier. The double negative is the same as leaving it alone. Okay, and then actually we're done because I'm going to use the same law again. So this is scratchbook over here. Now I'm going to use this law again, but in reverse. So it's going to be a bit tricky. So in reverse, the way I should think about it is if I have the negation of something or something else, I can turn it into an if-then. Well, I have that. I have the negation of this thing. So that's acting like my P over here. So I have a negation of something. Or something else. What's my something else? What's my Q? My Q is this whole thing. And so that means I should be able to turn it into an if-then where this guy is the if and this guy is the then. So this should turn into this, if that, then that. So that's exactly what we're doing here. If the underlined red part, then the underlined blue part. And that's it. That's what we wanted to show, right? That's the whole law. This is the contrapositive of the original statement. You negate both and you switch the order. And we've shown that it's equivalent to the original. Okay. So that's the end of the proof. All right, so later on, we'll see how this is useful. So I'm not going to do a proof using that right now, but something like this, if I wanted to prove a statement like, if x is odd, then x squared is odd, pretend like I have no idea how to prove that, but in some weird way, it could be easier instead to prove the equivalent statement, the contrapositive, if x squared is not odd, then x is not odd. In this situation, it's probably not easier to do that, but other situations it will be. And because they're the same, I could do this proof instead of the original, and that would be equivalent. So then that would complete the proof. Okay, so that's for later. We're not going to do that right now. Today is more about practicing using these laws, creating more laws for previous ones. So let's keep doing that. Okay, here's another one. Show if P, then Q or R is the same as saying if P and Q don't happen, then R will happen. This one's a bit weirder, so I'll write another example sentence after we do the proof, but it's also very useful. Okay, so let's do the proof. So this time I'm going to start with the one on the right and work my way to the left. All right, so, oops, so what do we know about something like this? Well, it's an if-then, and I already have rules about if-thens, so why don't I use them? What's the rule I keep using? I keep using this rule, that an if-then is the same as not the first thing or the second thing. So I'll use that. So what's my first thing? Instead of just being P, it's this whole thing. So it's not that or the then part, right? That's my Q in the little equation I have up here. Okay, so that's what I'm using there. So then what I can do, well, I have another De Morgan's law situation because I have a negation outside of an and. I can put it through and switch the and to an or. Then I get that. And then I have a double negation on that Q, so I can just make that be Q again. That's it. And now I'm in a sort of weird situation because I have this or that or that. And I guess what I should have been doing the whole time is keeping these parentheses like that because these were together. But the or operation is actually associative, and that means I can rearrange these parentheses to be like that instead. Now, I didn't write this property down, this law down earlier, or name it, just because it's a law that you're very used to, even if you've never really used it or thought about it too much. But you're basically just saying like 5 times 2 times 6. I can think about it like that, 5 times 2 times 6, or I can think about it like this, and they're the same. The or statement works the same as this. If I have 3 different things and I say this or this or this, you can't even tell the difference between if I say this or this versus this or this or this. They sound exactly the same, and they are the same. So we can rearrange our parentheses, and we have or statements. So that's what we'll do. And now we are back to using this law. It's a very important law that I keep using because I have something that looks like this on the right. I have a not something or something else. So that becomes the first thing implies the second thing. And then we're done. That's what we wanted to show. Right? That's the thing on the left, starting from something on the right. Okay, so this ends the proof. So let's do a little example of this one. So you could say something like this. If 3 divides A times B, so that's my P statement, then 3 divides A or, 3 divides A or 3 divides B. And for some reason or another, this might be hard to prove. But now we know it's exactly the same as saying if what? If P and not Q together, then R. So maybe I'll label these. So this is P. So if P, then Q or R should be the same as P and not Q happening implies R. So if 3 divides A times B and Q doesn't happen, so 3 does not divide A, then R happens, 3 divides B. So let's try to convince ourselves that these two statements are the same statement. So in the first situation, you're saying, okay, 3 divides something times something. Then 3's got to divide one or the other. That's got to happen. Versus, okay, 3 divides something, a product, but it doesn't divide one of them. It doesn't divide A. Well, then it must divide B. Why is that the same as the original? Well, that's what this proof is for. It's because if you know it divides AB and you pretend it doesn't divide A, then in order to divide A or B, it's now got to divide B because you're taking away the possibility of it dividing A. And that's another useful proof technique that we're going to do later. Okay, so this will also come in handy a lot later. For now, again, we're just practicing being able to do this kind of stuff. But you should write down other sentences like this and try to translate them and convince yourself that they're saying the same thing. Okay. All right, so here's 2 more very important laws. You could call them distributive laws because they sort of look like how multiplication distributes over addition. So for example, this is a law that you're familiar with, except the laws here are a bit weirder because it turns out that and or both distribute over each other. So for numbers, multiplication certainly distributes over addition like this, but the reverse is not true. So if you try to distribute plus over multiplication, that's not going to work out for you. It doesn't work like this. But for and or, it does work like that. Okay, so I'm going to write it out. And if you want to prove it, you have to use truth tables. So it's a good exercise to do. I'm not going to do it because it's going to take much too long. It's just more useful to use the laws. So this is saying that and distributes over or. So it goes into it like that. But then we can do the reverse, or also distributes over and. So it looks very similar. So you could write down some sentences in English, and it's not going to work out that nicely, unfortunately. So you could say, no, I'm not going to try. I will put some on the lecture problems instead. Once I make them, because they'll make more sense in writing than they will verbally. Okay, but anyway, if you want to prove these, you'd have to use truth tables. And the annoying part is that since you have 3 statements, you'll have 8 rows because there's 8 different ways P, Q, and R could be true and false at the same times. So yeah, the main purpose of showing you these 2 laws is just because they're cool and they're different from the laws that you're used to about addition and multiplication interacting with each other. Okay, and there's plenty of other laws, but that's going to be it for today. Okay, see you next time.